So in biology, percent solution is usually in grams per milliliter, where the solvent is the compound and it is dissolved in the solvent water. The solvent is added to less than the required end amount of water, dissolved, and then the volume is increased to the correct volume, called quantity sufficient, or QS for short. In this system, an example 1% solution is 1 gram of solute dissolved completely in 70 mils of nanopure water and then brought to a final volume, QS, of 100 milliliters. So, today we're talking a bit about, in biology, when we're using percentage, what sort of assumed standard are we following? And so when we say something is a percent solution, we're saying it's grams per usually 100 milliliter of nanopure H2O, which is just very, very, very clean DI water. And so we'll have grams over 100 mils of nanopure water. And so a 1% solution is, let's say 1% is 1 gram per 100 mils of water. Now you don't go all the way up to 100 mils because if you're dissolving something, it will displace some of the water, and this displacement factor will change a little bit as it is dissolving in it. And so if you have to use a stir plate or a stir rod or a magnet or what have you, you use less than the amount of water that you ultimately need to get to dissolve as much as you can in it, and then finally you QS up to the required amount. Now, unless it's said otherwise, you are assuming that this percentage is over 100 mils because percent is per 100. So let's just hop right into some examples that we have going on here. So again, it's grams per mil. And so for these first 5 examples, we're going to be using sucrose as the solute that we are dissolving in our water solvent. And so we have the situation set out here. Let's start with the first one, 15% solution in 100 mils of H2O. Now it looks like we've only been given 2 points of data, but we've been given 3. And so a lot of these problems end up looking like ratio problems, where you have one fraction set equal to another. And so let's just start with that. We know that the definition of percent solution is grams per milliliter with the 100 mils underneath as the assumed quantity because it is percent or of 100. So 15% solution is 15 grams per 100 milliliters. Fantastic, we have mass over volume. And there are pure mathematics out there, and mathematicians in general, and chemists who are not happy with this, but in biology, typically our universal solvent is going to be water, because we're working with, again, biology, and so a lot of us are very, very liquidy in biology, and our liquid is water. And so this works for us biologists, particularly in biotech. And so 15 grams per 100 milliliter. And then we do have one more piece of data. We have our fraction. We have 100 mils as the end. Now, this one's pretty straightforward, right? Pretty straightforward. It was pretty much given. 15 grams over 100 mil is equal to what over 100 mil? Well, the only thing x can be equal to is 15 grams of sucrose in 100 milliliters of H2O. And there's our answer. And so if we were in the lab, we would go out, we'd find ourselves the sucrose, we'd weigh out 15 grams exactly, dump it into about 70, maybe 80, maybe even 90 mils of nanopure, mix it, and then QS it. But we're not in the lab, we're at the computer, and so here we are. So let's move on to the next one. 6% solution in 300 mils of H2O. I'm going to do the same thing. 6% solution, we know that percentage is grams per mil, and since it's percent, it's 6 grams per 100 milliliters is equal to, again, we don't know how much we're actually weighing out. We have an X mass times 300 milliliters. Now, this time isn't as clear, and so I'm going to cross multiply, and then I'll have 6 grams times 300 milliliters is equal to X grams times 100 mils. I want to get X by itself. Let's, there we go. 100 mils divided by 100 milliliters divided by 100 milliliters. Milliliters and milliliters cancel. We're left with grams. And in this case, X is equal to 18 grams of sucrose in 300 milliliters of H2O. All right, let's do another. We have quite a few, and so we'll get the hang of this. Again, 12%. Okay, so we're going to do 12 grams per 100 milliliters is equal to 2 liters. All right, so we have liters now. This is breaking with what we understand, right? And so we're going to have to turn liters into milliliters, and so we can do a little scratch work. We have 2 liters, and then we have a conversion factor of 1,000. Oops, I'm sorry, I did that backwards. Of liters, whole number over 1. We want 1 liter down here. There we go, and that's why we still sometimes do that. And so since we have the equivalency factor of 1 liter is equal to 1,000 milliliters, all I'm doing is changing the units on this, but 2 milliliters is not the same as 2 liters, right? And so we're using this. And so we have 2,000 milliliters, and that's what we're going to use to plug in over here. We have a known volume that we just changed into a unit we can use, an unknown mass that we're going to be weighing out in the lab, and again, we can cross multiply. And so we'll bring the 2,000 over here. We'll do 12 grams times 2,000 milliliters is equal to X times 100 milliliters. Get X alone. Cancels that out, divided by 100 milliliters. Milliliters and milliliters cancel each other out. And so we have X is equal to, let's see, a 12% solution, 12 times 2,000, and we're looking at 240 grams sucrose in, what did we say? 2 liters H2O. Not too bad, right? Not too bad at all. And so we'll do another one. I'm going to skip the 25. So I'm going to skip that real quick because I'm running out of room. I squished myself in a little bit too much. And we're going to do the 14 right here. So again, 14 grams over 100 milliliters because it's percent solution is equal to, we have mils again, an unknown mass over 250 milliliters. Get X by itself. You can do the slow step-by-step, or you just know it's going to be pulled over 14 grams times 250 milliliters. The X and the 100 will be attached. I'm just going to jump ahead and go 100 milliliters right over is equal to X, and so X is equal to mils and mils, grams only, and we've got a 14% solution. We're looking at X is equal to 35 grams sucrose in 250 milliliters of water. Not doing too bad, right? Not doing too bad. And so another applicable thing is agarose and SB buffer. And so Agarose is the solidifying factor when we're talking about gels for running electrophoresis. And so this is something that you'll do a lot of as well if you make your own gels, either because they're very picky, or you need the practice, or you can't afford a bunch of new gels, or what have you. And so let's continue on. Although the solution of SB buffer has changed from water to this buffer, and we've changed sucrose to agarose, the math is still the same. So we're still going to set up this percentage as 1.2 grams over 100 milliliters. And we're going to put that equal to 200 milliliters of SB buffer now is equal to an unknown X quantity. Again, I'm going to do this cross multiplication the quick way. 1.2 grams times 200 milliliters over 100 milliliters. Cancel. Is equal to X. X is equal to 2.4 grams of agarose in 200 milliliters of SB buffer. So your answer in the end is the only thing that's changed. Not too shabby. Not too shabby, right? All right, let's do it again. 2.5 grams, 100 milliliters is equal to, again, mils, unknown quantity that we're going to weigh out, 300 milliliters of SB buffer. Quick cross multiplication, 2.5 grams times 300 over 100. I know these mils are going to cancel out, but it's still good to show that you know what you're doing. It's equal to, oops, X. And so we have X is equal to 7.5 grams agarose in 300 milliliters SB. All right, only two more. Now you may be asking yourself if these decimals are going to change anything about, particularly if it's under 1, of your fraction. The answer is no. No, just put it over a fraction and you're good to go. There's no need to convert this into its own form of decimal and then try to put that decimal on top of the 100 milliliters, because this would really be, you could turn this into a fraction of 2 1/2 over 100 milliliters, and then you have to deal with this fraction on top of that fraction, and don't do that. There's no need. This is fine. So 0.8 grams, again, percent is defined as grams per mil, per 100 mils, excuse me. X, 60 milliliters of SB buffer. Quick cross, 0.8 times 60 grams. Don't forget your units, because in this case we go immediately to the real world, and so we must be careful. 0.48 grams agarose in 60 milliliters SB. And last one, I'm sure you've got it by now, but 1.8 grams, 100 milliliters for our 1.8% solution is equal to some unknown X. Ooh, we're okay, there we go. 150 milliliters. Quick cross, 1.8 grams times 150 milliliter over 100 milliliter. Scroll down a little bit. Looks like I went a little bit off screen. And so we have 1.8 grams times 150 milliliter. 100 milliliters is what we've got going on down here, is equal to X. X is ultimately equal to 2.7 grams agarose in 150 milliliters SB. And there we have it. There's a quick little run through. These are pretty straightforward. You'll find that you do actually quite a lot of these quote-unquote straightforward dilutions and solution creation. You start with some known solution percentage, and that's all you have to work from in order to make its equivalent in whatever volume you are working with. Because that's the situation here, right? We have a rule that helps us solve what we're doing. We need 15% in 100 mils. We don't want to do the whole, oh, that's not a good example because that's straightforward. We don't want to do, let's say, 6% in 300 mils. This can be a doozy to figure out mentally, and so setting it up like this algebraically, particularly for those who are familiar with maths and who have been doing it for a while, or people who are just now starting out in their math career, this is a good, safe way to set all of these problems up to 1, have a breadcrumb trail, 2, follow your own work, 3, be confident in the answer you get, and 4, have proof of what you did and why. So if your reasoning and rationale are called into question, this is a really straightforward way of showing how. So, good job.